So this week, we are looking at foundation models and multimodal models. These are not distinct things, but they are not equal things either. Okay. But these are really the summit, the Mount Everest of deep learning today. These multimodal models are the most advanced, most capable, most interesting models that deep learning has produced. So I think I learned a lot, and I really had fun preparing these slides because they are very relevant and they have very interesting capabilities. So let's look at them together. But first, a brief recap of last week. We looked at large language models, and as you remember, the backbone, the modeling approach of large language models today is mostly autoregressive modeling, which is next token prediction. You can factorize the joint probability of a sequence into a product of marginals, shown on the left. And this factorization is exact, coming from the chain rule of probability. And then you can approximate or model each conditional here using a neural network model. It could be a RNN, it could be a decoder-only transformer, it could even be a CNN or MLP. You can design it, you can do it. What it does is it takes the elements before the current element, and based on them, it tries to predict the next element or the current element, however you look at it. Modern LLMs model this conditional probability using decoder-only transformers, and during training, you need to use a causal self-attention mask so that a token at location I does not attend to future tokens at locations larger than I. So this is the basics behind LLMs. We looked at the GPT family from 1 up to 3.5 and ChatGPT. And along this journey, I think the first three is mostly about unsupervised pre-training on more and more data. Wikipedia, Common Crawl, books, lots of things. But Instruct GPT was really made a major difference because in that paper they created, they fine-tuned GPT on supervised, well, it's actually here, okay. So in step 1, they collected demonstration data. This means questions and answers written by human annotators. And these are really open-ended questions. They are brainstorming questions, explanation questions, mathematics questions. They fine-tuned GPT-3 or 3.5 on this demonstration data. This is called the supervised fine-tuning part. And then use that model, they fine-tuned GPT-3, use that model to create several outputs given a prompt. So you give it a prompt, and then this model generates 4 different outputs, let's say. Maybe you see it sometimes in ChatGPT. Sometimes it generates 2 responses, and then it asks you which one do you prefer. So they are still collecting data from you. If you prefer response 1, it is probably maybe verified by some human, I don't know, but then it is used as a training example within this pipeline. So GPT-3 supervised fine-tuning creates multiple answers for the same prompt, and then a human sits down and ranks them from best to worst. We are also doing this, as I said. You see 2 responses and you rank them. You prefer one of them. And then using these preferences, they learn a reward model. And the reward, what does it do? A reward model takes in a prompt and an answer, and then gives out a scalar value as reward. So if this answer is good, it gives a high value. If this answer is bad, it gives a low value. And then using that reward model, they, in step 3, train the model further using reinforcement learning, and we will look at this next week. But it's basically, in reinforcement learning, there is this credit assignment problem, which is the main challenge. Let's say you are playing ping pong with AI, okay? You know that simple ping pong game, right? There are 2 rackets and the ball is coming back and forth. And then if you win the game, the sequence of actions that led to the win is taken as a successful game, but you don't know the label of each action you made. There is no supervision for that. The only thing you know is you won the game, and you know the actions you took based on the states of the game, but nobody tells you that specific action I in the ith step was a good move or bad move. Nobody tells you that. The only thing you know is you won the game. That's the credit assignment problem. You won the game, but you don't know which actions were led to the win, and which actions were good, which actions were bad. You don't know. And reinforcement learning basically solves this problem, I think in a very naive way, but we'll discuss it next week. So they use this reinforcement learning approach where, as the model is generating the response, 1 token at a time, you can calculate a reward, right, based on the current output, and then you use it to further fine-tune the model. So among the GPT line of work, Instruct GPT was really the made a major change, and today ChatGPT is using, and many other LLM deployments use this type of training pipeline. We looked at low-rank adaptation because suppose that you take a LLM like GPT-3. Well, GPT-3 is not open weights, it's closed. But there are equivalent open LLMs such as Llama, Qwen, and models from DeepSeek. You can fine-tune them to your domain, to your, let's say, data in your company, by using this low-rank adaptation method. It's a way of fine-tuning the LLM, but in a parameter-efficient way, because your GPUs probably cannot train the whole model because it won't fit in memory, the gradients, the momentum vector, and so on. To prevent that problem, instead of learning the whole weights, you create an auxiliary branch, A times B or B times A. You add them to the original weights, and the thing is, B times A is a low-rank matrix because of this R here. If you choose a small r, it could be as small as 1. If it's 1, then it's a rank 1 matrix. So the number of learnable parameters is much lower than learning the whole or fine-tuning the whole model. So it's a very nice technique for parameter-efficient fine-tuning of large models. Not special to LLMs. If you have a giant CNN and you want to fine-tune it on some data set, you can apply this LoRa technique there as well. It doesn't have to be LLMs or anything. And then we briefly touched upon concepts such as retrieval augmented generation and chain of thought, the thinking mode. And we introduced 2 open LLMs. And then there are, of course, others. But that was it for last week. Any questions about last week topics? Any comments? Okay, let's start today's lecture. We will first define what a foundation model is, and then we'll define multimodal models. And then the rest of the lecture, the bulk of the lecture will be about really how do you obtain a multimodal model using unimodal models. And this is the key challenge in large multimodal models, how to combine modalities. Early approaches like stable diffusion and control net, they condition diffusion on text, so image to text to image generation, edge maps, semantic maps, human pose, etc. And you can think of these things as different modalities, right? So it's a way of, it's actually a multimodal model. You are combining different modalities with the vision image modality. We will look at two approaches here. Stable diffusion, very famous paper. They use the cross-attention approach. Control net is another very famous technique, very impactful in the literature. And then we will look at how to obtain large multimodal models from a frozen language model, a frozen vision encoder, and then you need to somehow connect them together, glue them. And there are different ways to do that. Lava uses a simple linear projector. It takes the vision tokens and then learns a projector so that the vision tokens are now projected into the language model's token space. So they become like word tokens. Blip2 is taking a rather complex approach called Q-former, which is querying transformer, where you basically take the vision tokens and translate them into the language of the language model. So it's a little bit complicated, but I will try to explain it. Flamingo is using gated cross-attention. It's actually similar to the cross-attention approach of stable diffusion. You know, when we say self-attention, there is a sequence and attention is applied within the sequence. When we say cross-attention, there are two sequences and tokens in each sequence attend to other tokens in the other sequence. Okay, so that's cross-attention. And Flamingo is using cross-attention between vision tokens and language tokens, and thereby obtain a large multimodal model. There are many other ways to combine modalities. One recent example is this Janus-Pro, that is also from DeepSeek, I think. Janus-Pro is from DeepSeek. So we will look at that. Unlike Lava, Blip2, and Flamingo, Janus-Pro can also generate images. So it's interesting. It's an interesting model. And then we will end with a touristic walk through state-of-the-art multimodal models. They are really very interesting. I really enjoyed walking through all of their web pages, and we can do it in class too. Okay, so what is a foundation model? It was defined actually in a 2021 report, not long ago, 4 years ago. It's a report from Stanford on the opportunities and risks of foundation models. And they defined foundation model as follows. It's any model that is trained on broad data at scale, generally using self-supervision, that can be adapted to a wide range of downstream tasks. And at the time of the report, the current examples for foundation models were BERT, GPT-3, and CLIP. All of them we have seen in class. We discussed all of these in class. You should be able to explain the differences between BERT, GPT-2, GPT-3, and CLIP. Right? You know this. You should know this at a very high level. BERT is an encoder-only transformer. It is used to compute or extract representations or embeddings from documents or sentences or paragraphs. GPT-3 is the ancestor of ChatGPT. It's a decoder-only transformer trained using autoregressive modeling. So it's basically next token prediction. So BERT is not next token prediction. You know this, right? I'll just show you this. And CLIP is a multimodal representation alignment method. You have a vision encoder, you have a text encoder, and these output some embeddings. CLIPS tries to align them, makes them as similar as possible if these are matching image and captions. All of these models were trained on broad data, broad meaning, first of all, multiple modalities. So CLIP is vision and language. Okay, BERT and GPT-3 are not multimodal, they are purely language, but large-scale data, large-scale training is what distinguishes these foundation models from other models. Another thing is they can be adapted to wide range of downstream tasks. So let's look at, remember actually, what these models did. Let's look at BERT first. It's encoder-only transformer model. You feed, for example, it shows the next sentence prediction and masked language modeling training objectives in this picture. So if you remember, you give a sentence to BERT, you randomly mask some of the words, and BERT is trying to predict that masked words. It is masked language modeling. Another objective was next sentence prediction. You give it two sentences, and the model decides whether the second sentence logically follows from the first sentence. If it doesn't, it says no. If it follows, it says yes. I believe this NSP is next sentence prediction, probably. And you do this training on large amounts of data. At the end, it gives you a transformer model which can compute very useful embeddings, and you can use them in different language tasks. And at the time work was out, it achieved state-of-the-art results in many tasks. This is the pre-training data it used. Books corpus, 800 million words, and English Wikipedia, it has more words. So trained on large data. So the first criteria for being a foundation model, and the second criteria for being a foundation model is that BERT can be fine-tuned with just additional output layer, just one additional output layer to create state-of-the-art models for a wide range of tasks, such as question answering, language inference, without substantial task-specific architecture modifications. So we have two criteria for being a foundation model: training on large-scale data and being adaptable to downstream different tasks without too much fine-tuning or training. So BERT, in that sense, is a foundation model. Let's remember GPT-3. This is a decoder-only transformer model trained using autoregressive objective. And its training data, as you can see, it's again very large. This time it's in the billions. Previously BERT was millions, but this is billion tokens. So common crawl is a very large. It's actually the whole web common crawl. Web text 2 is a curated, cleaned, deduplicated version. Books and Wikipedia. And then, they trained this on this massive data set using next token prediction. And then they evaluate the resulting model on, for example, these data sets which are actually completion tasks. So in Lambda, you are given a paragraph, a couple of sentences, and your model needs to predict the last ending word. So it needs to complete the missing last word. It's a completion task. And close task is similar. It's this time it's story. You are given a 4 or 5 sentences story, and the model needs to choose the ending sentence. So these are completion tasks. And as you can see, GPT-3 outperformed or performed comparable to state of the art in its time. So these are good results. And what it introduced is zero shot, one shot, and few shot modes. And zero shot means, let's remember, you only give the task description to it. Only give task description, such as translate from English to Turkish. You just give this prompt. This is called zero shot. You don't provide any examples for the task. This one is task description plus one example. And this one is, as you can guess, task description plus few examples, like 3 examples. Okay. And this is...
This example is not in pre-training process, right?
No, in the prompt, yes. It's not in pre-training. And they are saying that these tasks, so for example, in the next slide, they evaluated on open domain question and answer tasks. And it is not specifically trained for answering these questions. Because look at the data set. Common crawl, web text to, well, this is coming from, remember, from Reddit, right? And in Reddit, there are lots of questions and answers. So GPT-3 was this paper really introduced the in-context learning. So we call this, these are important concepts, right? In-context learning. So whatever you give to the LLM, we call it prompt, but in the prompt, you usually give some prior information, and then at the very last, you may ask a question. And you can call that question as a prompt, but this part is context, the information that you provide. And in-context learning is you provide examples in your prompt. And this is kind of lightweight learning, as this paper shows. Again, it performs well on open domain question answer tasks. It outperforms neural machine translation, so language to language translation using neural networks. Yeah, it outperforms. I don't see bold numbers here, but it at least performs on par without being explicitly trained for translating these languages. So again, large-scale training and adaptable to many different downstream tasks. So it's a foundation model. Okay. Yeah?
Are there any metrics that measures the relation between token and brand? Let's say in my prompt, I write it less token and give the yearly statements.
So you are talking about the number of tokens in your prompt and the accuracy of the model. I don't know. There are papers on number of tokens in the pre-training data set and the performance on downstream tasks. And we call them scaling trends, actually. These are scaling laws, even. But I'm not aware of any paper which examines the number of tokens in the prompt and the performance. Okay, and then the third example was clip. It's not an LLM, and it takes vision encoder, text encoder, and it does representational alignment. It tries to make the embeddings coming from the text and the embeddings coming from the image as similar as possible. As you remember, it used image caption data sets such as Lion 5 billion as its training data. So again, massive pre-training data set. And then out of the box, without any further fine-tuning or in-context learning or further training, it can do zero-shot recognition on many data sets, and it outperforms the linear probe on ResNet 50 on, I think, 11 data sets out of 27. And there are also other downstream tasks that are given in the paper. So this also qualifies as a foundation model. Massive pre-training and adaptable to downstream tasks. So a foundation model is a model that takes in massive amounts of data in multiple modalities. This could be text, image, speech, structured tabular data, or data coming from sensors, so signals. You train this model on large amount of data, typically multimodal, and then what you obtain is a foundation model which can be adapted to downstream tasks such as question answering, sentiment analysis, information extraction, and so on. This figure is from the that report that I talked about. This is the report which defined what a foundation model is. As you can see, multiple modalities is central to the definition of a foundation model. They emphasize this. A foundation model uses multiple modalities, and that's very important. So let's define multimodal model too. A multimodal model is a machine learning model that represents, processes, or generates information from two or more distinct data modalities. This could be, example, text, image, audio, video, depth, sensor signals, etc. Either jointly or through cross-model interactions. Okay. Most foundation models are multimodal, but we cannot say that foundation equals multimodal. So they are not the same thing. But most foundation models are multimodal. There are unimodal foundation models too. GPT-3 is the obvious example. It's a foundation model, but it only works on language, so it's a language foundation model. But there's also vision foundation models, such as Dino. It has 3 versions, right? V1, V2, V3. So they don't have to be multimodal. They can be unimodal, but most foundation models are multimodal today. They become more interesting when they are multimodal. And vision language models dominate the term multimodal today. When we say multimodal, we almost always mean vision and language. But multimodal/foundation models exist for several other modality combinations. For example, there are vision, 3D objects, humans. There are audio language multimodal models. There are audio, vision, and language models. Sam Audio was actually released 2 days ago. We'll look at it. Sam 3D was released 2 or 3 weeks ago. So it's very recent too. Whisper in, I think, 2022. Video foundation models or video multimodal models. VJEPA. Jan LeCun is advertising this a lot. This is also not very old. This is recent. There are biology, science, foundation models such as AlphaFold. Right? We discussed AlphaFold, I think, in the first week. It really made a huge impact in biology, how amino acids are sequenced and how the shape of the proteins, 3D shape of proteins are predicted. Previous to AlphaFold, studying just one protein took one PhD for 5 years, but now it's 20 minutes and it's better accuracy. And there are also sensors and embodied modalities such as vision, language, action models like Gato is actually more than that. But robotic transformer 2 is a vision, language, and action model, which is also very recent. So at the very end, we will look at each of these on their, we will click these links and we will look at these web pages. And there are very interesting information on those pages. But first, we need to understand how multiple modalities are glued together, right? That's the main challenge in multimodal modeling. In this class so far, we have seen 4 foundation models, CLIP, Dino, BERT, and GPT-3. And in the previous slides, just a few minutes ago, we remembered CLIP, BERT, and GPT-3. Now let's also remember Dino. Dino is actually a very simple idea, which is shown on the left. X is an image. You take it from a data set, and this is unlabeled. You create 2 randomly augmented views from this image. These random augmentations can be a little bit of translation and cropping, adding color distortions, and so on. So randomly augmented views, X1 and X2, but they're coming from the same image. One of them goes through the student network, the other one goes through the teacher network, and these are the same architectures but different weights. Student will be updated by backpropagation to minimize this cross-entropy loss, but teacher is the exponential moving average of student. At a very high level, the teacher network processes one of the augmented views and creates P2, which is a probability vector, because it's the output of softmax, over a chosen number of classes, capital K. And this is an hyperparameter. So it basically creates a kind of a label for X2 in a K, capital K dimensional class vector. The job of student is to, again, through the softmax, produce a probability vector P1, and basically you want them to be as similar as possible through minimizing the cross-entropy loss here. Dino used, the original Dino V1 used ImageNet 1K as a training data set. It has 1,000 classes, but class labels are not used. It has 1.2 million images. So it is considered a large data set. So large data set pre-training. And then it is, Dino features can be used for many downstream tasks. So 2 criteria for being a foundation model are checked. First, massive pre-training and adaptable to downstream tasks. Later, with Dino V2 and V3, this is further improved. Dino V3, for example, this is also very recent. It was released this year, I think, a couple of months ago. They used this LVD data set. It's a curated data set of 1.7 billion images extracted from a large data pool of 17 billion web images collected from public posts on Instagram. because this is from Meta. They own the Instagram photos. Plus ImageNet 1K, ImageNet 22K, and this mapillary street level sequence images. So trained on massive, huge data sets. Later, when you fine-tune, when you use this Dino features, because what does Dino do? You give it an image, it gives you an embedding. And you use those embeddings for different things, such as object detection, semantic segmentation, monocular depth estimation, etc. So you can adapt these embeddings to different downstream tasks, and you obtain state-of-the-art results. So, foundation model. And it's unimodal, it's not multimodal. There are no language or other things here. Okay, any questions so far? Now let's talk about the main problem in multimodality. How do we connect or combine different modalities? There are many ways to do it, and we will go over some of the prominent approaches in the literature. The early approaches in diffusion used, so we conditioned diffusion on text, edge maps, semantic maps, or human pose, using two different approaches. The one proposed in stable diffusion used the cross-attention approach, and ControlNet used the ResNet-like approach. So we will look at them. And then modern ways of combining modalities is what the large multimodal models do, such as Lava, Blip, Flamingo, and Janus-Pro. Okay, so let's remember diffusion, right? In the forward diffusion process, we take an image, we add noise to it, and then we obtain a noisy image. And I know exactly what noise I added to this image because I created this noise image. Now the task of the denoising model, denoising UNet, a UNet is used. Maybe we didn't talk about the UNet, but it's this CNN architecture which has this shape. You first take the image and then decrease the spatial resolution of your tensor, and then you take it up. So it's UNet. You have connections in between downsampling and upsampling layers. So the task of the denoising UNet is to predict that noise added to the image. So that was DDPM. But stable diffusion, it was in CVPR 2022. It proposes to do diffusion on latent representations, not the image pixel space. DDPM, which we have seen previously, applied diffusion on pixels. Stable diffusion applies it to latent representation of image. What do we mean by latent representation? Remember variational autoencoders? There's a encoder and a decoder. And when the image passes through the variational encoder of the VAE, you get this latent representation. It's like a compressed version of the image, compressed contents of the image. And this is what the E here does. It's a encoder coming from a variational autoencoder. And you pass your image X through the encoder, and now this Z is a latent representation of the image. It's no longer pixel space, but some representation of the image. Stable diffusion applies diffusion in this latent space. That's the difference between stable diffusion and DDPM. So forward diffusion process takes the clean latent and noises it to obtain Z capital T. And then the task of the denoising unit is to this part. Take the denoised Z capital T and then predict the noise within that, so that you can use that prediction to denoise your noisy images and eventually arrive at Z. And of course, once you arrive at Z, it's still in latent space. You need to convert it to pixels, and there you use the decoder of the VAE, this part, which gives you the image in pixel space. So this part is the plain diffusion, the vanilla diffusion applied on latent representations obtained using encoders, VAEs encoder. What they do differently is they use conditioning here, modalities on the image generation process. For example, they use a semantic map or text or other representations or even images. They use it by, so a diffusion model generates an image, but you also, if you also give it some text, so generate a cute, a photo of a cute cat, for example. This is text conditioning. You input text as condition. That text passes through another encoder, which is called tau, and this will be learned during training. This produces an embedding of the conditioning input. It could be text, a photo of a cute cat, now encoded through tau theta, and it's now a text embedding. You use it in two different ways, either concatenation, if you choose this path, or skip connection, or the cross attention if you choose other path. So they tried both of them, and the cross attention works better. So I will explain cross attention in the next slide, but maybe we can take a 10-minute break for now, okay? So how does latent diffusion or stable diffusion adds conditioning? Is basically you're adding this tau theta y as an additional parameter to the denoising network. That's it. Y is text, can be text. It can be a semantic map. It can be an edge map. It can be any conditioning you want. It goes through a learnable encoder tau, and then it produces an embedding, and that embedding is fed to the denoising unit as input. You can simply concatenate this to your Z capital T, or you can use the cross attention mechanism, which works better. And here you see the cross attention mechanism where that embedding from the conditioning is connected to many layers in the unit, and that it feeds into this query key value blocks. And let's now look at them. Those blocks implement attention, the usual query times key, softmax. This gives us weights, and those weights are multiplied with the value vectors, and at the end it gives us the weighted average of the value vectors. Here the key part is coming from the condition. So this is the condition. Think of it as text. So text is producing the keys, the values. So this is also condition. And then they interact with the ZT, which is the noisy version of the latent representation. And as you can see, it is cross-attention, right? Because attention is between the embedding of the condition, which is tau y, and the ZT. Or this phi IZT, which is the flattened intermediate representation of the UNet implementing the denoising network. So this is it. Simply you add an additional input to the denoising network. You can either use cross-attention to to make the embedding attend to image, or you can use concatenation. And at the end, what you get is this. When you give diffusion model this text as conditioning, a street sign that reads latent diffusion, it creates these images. A zombie in the style of Picasso, very successful. An image of an animal, half mouse, half octopus. I think it's very successful, and so on. And you might ask how this model was trained. We use the usual image caption dataset Lion, which contains billions of image caption pairs collected from the web. This is noisy dataset because on the web it's not, everything is not accurately labeled, but it still contains lots of supervision signal. So this is stable diffusion. Yes.
Do you have control over the text font of generating? Because they are all the same. It's very obvious that it's generated. You can have a condition for this.
Of course. Yes. You can do it. But what do you need to do that? Think about it. You need a training set.
On a specific test.
Yes.
Specific faults. Is that will be
I think so, yeah.
Oh, okay. How much should why like if the caption of the image?
Yes.
That's when I just testing, I hear some other things.
Yeah, in inference, you can just give anything. How does it generalize? The generalization power comes from the Lion dataset. 5 billion image caption pairs. Everything on internet. Inference, we start with? Yes. And the text prompt, why? And it generates, so here, these are Y's. This is Y. It passes through a text encoder, and then latent diffusion produces this text. I'm not sure, Yunus, it's all the same fonts because look at these. These are, I don't think these are the same fonts. And here also. You can test. These models are on the web. You can test. Generate this sign in Helvetica font, for example. You can check. Because in the massive dataset Lion, I'm sure there are font pictures, so font and caption. So it probably knows the fonts.
That's fine.
Mhm. A list of texts. Yes, you can.
As a simple paragraph.
As a simple paragraph, yes. Yeah. You know this, there are, I think if I can find, let's see. What was it called? Here. Okay, for example, this is not what I'm looking for. Maybe this one. Okay. So this is the prompt that they gave to the model, and they used Midjourney to create this image. And in some of this, I don't know, we need to find some of the captions are, text prompts are really, okay, this is not, okay. Some of the captions are really long. They give a very large caption, and it can generate images. So this is stable diffusion. You can not only use text, but also layout. For example, you can create this image layout where the black box shows the whole image, and then you put these bounding boxes with object classes. So you can say that I want a traffic light at this point, I want another traffic light, I want car, and so on. And then it creates an image that conforms to that layout. Here, train, tree, wall, concrete, flower, vase, table, and then it creates an image according to that layout. All you need to do is what you want to use as conditioning, you need to encode it so that it produces a vector, and then you can feed that vector into stable diffusion. And then, yeah. Mm-hmm. For what issues? Copyright.
As long as I know it can create this
Cannot create.
Yeah.
I don't know whether in this paper they did anything about copyright. I don't know. So, but how can you use it? How can you generate a training set for such a task? You want to give the layout, and it will create the image. Object detection data sets can be used. MS Coco has lots of images with these kind of bounding boxes. You can just use it to train stable diffusion. And it works. Okay. So another example, sorry. You can give it a semantic map where there's a category label per pixel. For example, this orange color is like the sky, gray color is trees, and this green is, I don't know, some lake, and then it creates this nice image which conforms to the semantic map. Okay, that was stable diffusion. You can condition it on text, bounding boxes, layout, and semantic segmentation. And then 1 year later, Control net was out in ICCV 2023. This paper adds spatial conditioning, such as in the form of edges, depth, segmentation, human pose, and controls large pre-trained text-to-image diffusion models. For example, if you give it a Kenny edge map like this, so it's an edge map, and then use this as conditioning, it creates these images. You can also give more than one conditioning, so this edge map plus captions as prompts, and then it will create image according to those conditions. You can input a human pose, a 2D human pose, where the joints of the human body are, and then it creates these human bodies, and you can add these additional text prompts with the human pose, and it creates the human in the same pose. So control net is really made an impact. Control net idea is still being used today. It's very impactful. And how does it do it? It's very simple. On the left, you see the control net idea. On A, this is the neural network block, which was pre-trained. You can think of this as stable diffusion. Adding control net to it means you add this trainable part here. And notice that it's very much like the ResNet idea. You are adding a branch which gets added to the output, and you have zero convolutions. This ensures that at the beginning this branch does not have any effect, but once you start training, this trainable copy gets trained, and then without modifying the stable diffusion here, it's all frozen, locked, right? It's not trained. You only train this additional trainable blocks, and you get the effects that I showed here. So instead of cross-attention in latent diffusion, in stable diffusion paper, they add this additional blocks, trainable blocks, and they add them in a ResNet manner, and they train this on data sets which are conditioned on, for example, sketches, normal maps, depth maps, Kenny edges, lines, HED, edge detector output, semantic maps, and human pose. And this adds a really good layer of spatial controllability on stable diffusion. So the techniques introduced in these papers are not really very novel or very interesting. They are actually very simple ideas, but I think the main contribution of these papers is that to show that this is possible. Right? You give a human pose, just a few points like this, and then it learns from a finite data set to generate images like this. Okay, I'm continuing. Now, let's look at large multimodal models. They bring together two or more modalities, hence their encoders or models. We will go through three examples, LAVA, BLIP2, and Flamingo, to exemplify modality connection methodologies. Okay. For example, LAVA uses direct projection, BLIP2 uses bottleneck querying, and Flamingo uses gated cross-attention, just like the stable diffusion idea that we have seen. We will also see Janus-Pro at the end. Okay, let's start with LAVA. It's short for Large Language and Vision Assistant, published in NeurIPS 2023. It's a vision language instruction following model that extends a large language model. They specifically use Vicuna, which is a fine-tuned version of Llama, and these are open language models, but the same thing as GPT, decoder-only, autoregressive, open language models. They use Vicuna. So they extend an LLM to handle images by mapping visual features into the LLM's token embedding space and then performing instruction tuning. So let's make it a little bit clear. Conceptually, LAVA is GPT-style LLM plus frozen vision encoder, which is they use clip vision encoder, and plus a simple linear trainable connector to project the embeddings produced by clip to tokens, LLM's token space. Here is the architecture. It's very intuitive, very easily understandable. You have a language model here, and this is, they used Vicuna here. I believe it's a fine-tuned version of Llama. They used clip. So at the beginning, it's frozen and it's never trained. So this is frozen. So at the beginning, language is also frozen, but in some of their experiments, they fine-tune the language model later. But this is trainable. They train this part. Huh? Yes. And then in the second stage.
They put the language models or instruction models.
Yes, you're right. So we take the image and then it goes through the vision transformer, which is the vision encoder of clip implemented by vision transformer. And at the end, you get this patch embeddings. You know, patches are tokens in images. So these token embeddings, and they go through this projection layer W, and you have this image tokens translated to the LLM's token space, a token space which LLMs can understand. So this projection W does the translation job to the LLM's language. And this part is the usual autoregressive, decoder-only, transformer language thing. You give it a instruction or prompt or a question about the image, and that gets tokenized, token embeddings, and these are the token embeddings here. You concatenate these things together and then feed it to a language model and let the language model do the rest. So it tries to autoregressively complete what would come next as a next token prediction, and that's it. So it's really a very simple idea and brings together two modalities in a very simple way. So it lets you ask questions about the image. I will give an example in the next slide. Let's look at the example. Do you remember this image from the first week or the second week? I told you that this was the Mount Everest of deep learning, the multimodal models. You give an image like this. By the way, this is a real image. It's not AI generated or anything. And you ask, what is unusual about this image? And then it gives you a very sensible, reasonable answer. So how does this happen? So it happens This is from the Lava paper. It happens using such an architecture. But the question is, how can you train this model? What kind of data set do you need? So you need a data set with images and question-answer pairs about these images. Do we have such a data set? You know? Hmm? What?
Social media is one of the styles.
Sorry?
Social media was
Social media. Okay, okay. Yeah. Could be used. Yes.
example like some.
Yes. But you need to be, I mean, how do you collect them? It's not easy.
You will conduct the exam and see what's up.
Okay. Huh?
I think in Lava games, data set that there is no data set.
Okay, I will explain. I want you to think now, what kind of a data set do you need? You need a data set with images and question and answer pairs about the images, but you don't have such a data set. We just have the Lion data set, like image captions, but it doesn't qualify as this image and then QA data.
Question and answer.
Because we want to, in inference during test time, we want to use it like that. I want to give an image to it and then ask any question about that image and then it should answer about the content of the image. But such a data set does not exist. And the main contribution of this paper, as you can see, is not this part. This is really a naive idea. Everybody can think of this. Making it work is the real task. So, and you need a data set to do that. It's called a visual instruction tuning data set, referring to the Instruct GPT paper. Remember the supervised tuning step 1? You provide demonstration data, so example, question and answers, but such data does not exist for vision and language. It exists for language, but it doesn't exist for vision and language. So creating that data set at scale, so we need a large data set, is challenging, but they created such a data set using pre-trained LLMs, and this was a major contribution of Lava. They actually used GPT-4 to create question and answers for a given image, but the thing is GPT-4 is blind. It doesn't see images. It started with GPT-4o. So GPT-4 is not a multimodal model, it's an LLM, it does not see images. Then how could they create this data set? This is actually very clever design by the authors. They used the captions dataset CC3M and MS COCO, which contain image caption pairs, lots of them. And in addition, MS COCO also contains objects and their bounding boxes. So you have a powerful language model, GPT-4, which cannot read images, which cannot see images, but if you provide a language description of the image to the GPT-4, then it can generate questions and answers about the image without seeing the image. So they fed the captions and object bounding boxes coordinates to GPT-4 and asked GPT-4 to generate question-answer pairs based on this information. The result is a large-scale visual instruction tuning data set called Lava Instruct 158K. So there is 158,000 images with associated question and answer pairs. And this is open. You can use it to train your own multimodal model. So here's an example of how they generated the data set. So there is an image coming from the MS COCO dataset or the CC3M dataset. Both of those datasets provide captions. And MS COCO provides 5 captions per image, and CC3M, I don't know, probably 1 caption, but it provides a caption. MS COCO, in addition, provides these bounding boxes. There is a person at these coordinates. There is another person at these coordinates, another person. There is a suitcase in these coordinates and so on, bicycle, car. So it gives you the list of objects in the image with their normalized coordinates. So you feed this information, caption plus object list and bounding box to GPT-4. So GPT-4 cannot see the image, right? This image cannot be seen, but its information is fed to GPT-4. And then GPT-4 creates this question-answer pairs automatically. So what type of vehicle is featured in the image? The image features a black sport utility vehicle. So questions and answers, question and answers. A detailed description of the image. Complex reasoning. What challenges do these people face? So these are generated by GPT-4, both questions and answers, without seeing the image. So very clever dataset idea. Another example, this time we only provide the caption, and I don't show you the image, which comes from the CC3M dataset. Just looking at the caption, you can create lots of question and answers. And then using this dataset, you train your LAVA model. First, you keep the vision encoder frozen, language model frozen, and only train the linear projector. And then they later fine-tune the language model to further decrease the loss. First the projection W is trained, and then they also fine-tuned the LLM. They used Vicuna. Standard next token prediction loss was used. That's it. Nothing else. And this is the result. This answer is generated by LAVA. It's really amazing because when you read this answer, you would think that vision is solved. These models understand everything because it's very difficult to come up with this answer. Any questions about LAVA? Mm-hmm. Of course it does, yes. GPT-4 makes mistakes preparing this QA pairs here. But most of the time it's correct, and that noisy mistakes are just, it's part of the data set. Lion dataset has lots of mistakes too. So noisy, learning from noisy supervision is something these deep models do. And if the amount of correct supervision is more than a certain amount, it seems to be working. So that's LAVA, yes.
Whether it's voice code or useful. So they just enter probes by hand. So do you give online?
They provide an API. So you use that API, but it costs a lot. I don't know where the authors are from, but yeah. They use the API. Yes, Mr.
This images.
Yes. How do they make the training work? Here. Okay, this one. So the image goes through the vision encoder, which is clip VIT. So image is patchified, embedded each token. And then those token embeddings go through the projection W. Now they become tokens that LLM can understand because now it's projected to a new space. You also give the token embeddings of your question and then concatenate them as a sentence. So image tokens, question tokens, and you feed them to language model. That's it. That's it. And then you train this to autocomplete for the answer. Very simple idea, and it works. The second method to combine different modalities is exemplified by BLIP, bootstrapping language image pre-training. It has two versions. We are looking at the last version, BLIP 2. So the key intuition is, now you know what Lava is. If you describe Lava as project vision into the LLM's token space, BLIP 2 is learn a small cross-model translator between vision and language. So instead of that simple linear projector W, BLIP 2 learns a more complicated translator. But still, it translates the image patch embeddings, image token embeddings to LLM's language, large language models language. They achieve this using something called Q-former, querying transformer. So image encoder is again clip VIT image encoder, and it's frozen. The patch embeddings are fed to Q-former. The main property of Q-former is that it learns a set of queries on this input, and those queries are fed to the large language model. I will talk about Q-former in a minute. The output of Q-former is fed to the large language model, and then now large language model can answer questions about the image and describe its content. Okay, let's look at the first stage in training, which is Q-former. We have the input image patchified, goes through the image encoder, which is the frozen clip VIT vision encoder. In the Q-former part, first of all, they use three training objectives: image text matching, image text contrastive learning, image grounded text generation. These are basically different loss functions that you can implement when you are given an image caption pair. So for this specific image, this is the caption of that image. And now you are creating this basically image text matching losses. The details are not really important right now. It's basically trying to match the image and the caption here. The important part of Q-former is that depending on your image size, it could be any size, right? You will get, for example, for this specific image, you will get 9 tokens here. 9 tokens, because in this image you have the patches are there are 3 by 3 patches, so it's 9 patches in total. So 9 tokens, 9 patches. But they always use 32 tokens here, which they call queries. So Q-formers, think of it like a translator module, which is a transformer itself, takes in a number of tokens and outputs another number of tokens. So it translates between n input tokens and m output tokens. So this is different than regular transformer. In a regular transformer, if it receives n tokens, it outputs n tokens. That's the self-attention transformer, right? N tokens in, n tokens out. But what Q-former does is that you can give any number of tokens as input, and you can extract any number of tokens as you want. This is a parameter that you fix. Here they use 32 tokens. So regardless of the image size. It could be a very large image, very small image. The number of tokens, the number of patches changes, but they always use these 32 tokens to compress, to summarize the content of the image. Their description is very complicated for QFormer. QFormer was introduced in Blip, but the important thing is it lets you change the number of tokens from input to output. Here, I want to give an example from our own publication in WACV 2025. I think we do a better job explaining it. This is for anomaly detection, but the part we are interested in is this part, QFormer. So from the input image, you get lots of tokens, but you want, let's say in the output, you want a fixed number of, regardless of the input image size, you want a fixed number of tokens at the output. That's what QFormer does. Here in this image, we are learning four queries or 4 learnable tokens. And at the end, regardless of what the input image size is, you get 4 outputs. So here is how it does that. Let's say this is input image token 1, input image token 2, and input token n. And let's call these output 1, output 2, output 3, output 4. So n tokens in, 4 tokens out. How does it do it? Within the QFormer here, it does self-attention and cross-attention operations. So let's call I the vector of input tokens, I1, I2, In. Let's call O the vector of output tokens, O3, O4. Now, within the QFormer, we do self-attention within the output tokens and also cross-attention between the input and output tokens. That's it. And it's actually cross-attention which lets you any number of tokens that you choose in the output. So Blip uses this QFormer to translate image tokens into LLM tokens. Here. So input image passes through the image encoder, frozen. QFormer converts this image into 32 tokens, and then this passes through a learnable, fully connected projection layer. And finally, these are fed to the LLM decoder, which is frozen language model. And both of the stages are trained using image caption datasets. There is no visual instruction tuning dataset such as the one used in Lava. So it's only image and captions. And the first stage learns QFormer. The second stage learns the fully connected layer. But it's essentially a very similar thing. Lava used a linear projector, a very simple thing, to project image tokens into LLM tokens and fine-tuned also the LLM. But here, they don't fine-tune LLM, but they use a more sophisticated approach to translate image tokens to LLM tokens. And the result is good. You give this image and this prompt. I think it does a good job. I don't recognize the car, but so these answers are actually good. You can also do conversation, a few round of questions. This is similar to the man ironing behind of a taxi. It understands that the man is scared of the chicken is flying at him, and so on. So that was blip. Now let's look at Flamingo, the third approach. This is another vision language model specially developed for few-shot learning. And here we are using in-context learning. So in the input prompt, we provide an image and the caption, another image, another caption, another image, and a half-completed caption. And the task is to complete this half caption given the examples in the input prompt. So it's an example of in-context learning. So for example, this painting, what is the title of this painting? So you have question and answer pairs in the examples, question, answer. And then question, answer will be completed by the Flamingo model. It is multimodal, as you can see, image and text. Key intuition is, if we think of LAVA as projecting visual features once, then treat them as text tokens, Flamingo is let the language model repeatedly attend to vision at every layer via gated cross-attention. So cross-attention is again the key here. And it's this model. The input images are passed through frozen vision encoders, and then the output is inserted. So this is a transformer layer here. Inserted as gated cross-attention layers between standard transformer layers of the LLM. Text tokens can repeatedly attend visual features during generation. So this is different from LAVA and blip, because in LAVA and blip, the image is processed once, tokens are translated into the language model's tokens, and that's it. The language model now uses them, does lots of things. But here, the output from the vision encoder can be used during inference as many times as the language model wants. It tries to attend them to the visual content. So the gated cross-attention layers looks complicated, but it's nothing but look at this pseudocode. It's very simple to understand. Y is the language features, X is the visual features, and here you implement an attention between language as query and key and value coming from the visual features. So this is cross-attention part. That's it. So this cross-attention is combined with self-attention, the usual language self-attention, using these gates. And remember gates from RNNs, LSTMs. These are things between 0 and 1 and with learnable parameters. So during inference, the model can shut off the gate or open the gate, and it adjusts how much of the cross-attention, how much of information from the vision is needed or should be consumed by the LLM. That's the idea. So no visual instruction tuning as in LAVA. It was trained mainly on interleaved image text sequences. These are coming from captions, web documents with images, video plus narration, and the objective is standard next token prediction. And this screenshot I took from the paper describes the data sets that they used. Look at that. It's 43 million from the 43 million web pages, they extracted text and images. And then they used 1.8 billion images paired with alt text, 312 million image and text pairs, 20 million short videos paired with sentence descriptions. When it is trained on such a massive data set, it can generate these kind of answers. Yeah, you can ask questions to Flamingo, and then it can answer these questions. Okay. Okay, now we have Janus-Pro left, and then we will just look at the web pages of the other multimodal models after the break. Yes. You cannot do it with stable diffusion, but it is possible to do it with maybe other things. Yeah, you cannot do it with stable diffusion. So you want to give a caption, it will generate an image, and you want parts of the caption. You want to know which part of the caption is related to which part of the image. This is kind of an explainability question. So I think you need to do something post hoc. So after it is generated, you can maybe give the caption and the generated image to a blip, for example, or some VIT plus text encoder, and see the attention between them. Maybe, I don't know. Okay, as we have seen, there are many modality combination methods, and lots of combination methods are possible. I'll just give another example here, which is from the Janus-Pro paper by DeepSeek. Unlike Lava, Blip, and Flamingo, they use different vision encoders for understanding and generation tasks. Here you see their architecture. There is an understanding part, the blue background, and there is a generation part, the yellow background. Understanding encoder and generation encoder are different. So that's, but other than that, of course, there are many details, but at a high level, these encoders produce image tokens, and this text tokenizer produces text tokens, and at the end, everything gets processed by an autoregressive transformer. This part is the language modeling part, and they probably use one of their own language models produced by DeepSeek. And then, unlike Lava, Blip2, and Flamingo, this model can generate images too. Text detokenizer. Okay, good question. Language response. Text detokenizer. So from the figure, I understand that to produce the plain language that humans can read, you need to convert these embeddings to the words. That's what detokenizer does. Yes, kind of a decoder for words, I think. But yeah, we haven't seen this concept before, right? Detokenizer. But I don't think this is something new that these guys propose. So this is the kind of tasks that Janus-Pro can solve. You can so give it an image and ask a question and get this answer. For example, this picture of a cake, and then can you introduce the background story of this cake, and then it produces a reasonable answer. This here also. And unlike Lava, Flamingo, and Blip, this model can do text-to-image generation. As you can see, these are the captions or the prompts given to the model, and these are the images generated. So image generation quality is really good. Okay, so this is slide 14 that I showed you today. Now, there are many multimodal models on the web today, which are state-of-the-art in their domains. Now, let's look at each of them one by one, and then try to get an understanding on what they do. So this is SAM3D, was released on November 19th, so last month, just a month ago. And the results are really amazing. What it can do is you give it a still image and then click on some region of interest, and then it creates the 3D model of that object, humans included. So look at this. So the buildings or this cars, it creates a 3D model and human 3D models of humans. And this, the accuracy of human body and shape estimation is much better than the state-of-the-art models that we had. So SAM 3D body is, it can create the 3D models of objects. Look at this. And also humans. So building on the knowledge that you have now some knowledge of multimodal foundation models, right? You can think of how this can be done, this kind of task. First of all, there needs to be massive amounts of training data. There needs to be multiple modalities, and you need to somehow convert those modalities to each other or to a common space so that a language model or a common model understand these different modalities, right? And here they show, it's an animation. You click on some points, give it to Sam, and then Sam gives you the segmentation masks, and then SAM 3D gives you the 3D object models in the form of mesh or Gaussians. So to train such a model, you need a massive data set of object and their 3D models, right? Otherwise, I didn't read the whole paper. This is just 1 month ago, but it is worth reading. I don't even know whether this model is open or not, whether you can use this in your own projects. Things from Meta are usually open weight. You can probably download it and use it, but I didn't check. Yeah, this is SAM 3D. Okay, I think you can use SAM 3D object, SAM 3D body, and so on. There's also a playground which you can upload your own images and play with the model. So it's very entertaining, highly encouraged. So this was SAM 3D. Let's look at an audio language multimodal model. This is from OpenAI. called Whisper. And look at this architecture diagram, which is which should be, I think, now very understandable for you, right? Because here on the left, the audio modality is given as input, and then it does some, of course, audio processing. But at the end, it creates this transformer type of representation of the audio with positional encodings and goes through many encoder blocks. And at the end, this is like the whole summary of the audio. This is fed to the decoder blocks in the decoder part of the model, and this creates the speech. So this is speech to text model. And its performance is really good. I think now you should be able to understand what it is doing at a high level, because we have seen some fundamental foundation models or multimodal models. Audio vision language, this was introduced 2 days ago, yeah, December 16th. Its results are amazing, actually. So can I open this audio here? Let's see. What's going on? I don't know. Yeah, you can check this yourself. You give it a video and then click on some region. For example, you can click on the train, and it gives you the sound of the train only. If you click on the human, all other background noise is suppressed, and you hear the birds sound. There is also text prompting. You can say dog barking or singing voice to extract specific sounds. So this is language, audio, and video. So 3 modalities together. This is the kind of the architecture diagram. See, they have some single modality alignment losses. So audio to video, audio to audio and text, audio, video, text, and then they have fused modality alignment losses. This is audio vision language, and let's look at some video model. VJEPA, Joint Embedding Predictive Architecture. Here, I'd like to show you this one. On the left, you feed some frames of the video, and there is 2 encoders. Can I stop this? I don't know. There are 2 encoders, and one of the encoders is updated using EMA, exponential moving average. So does it remind you of something here? This, huh? Dyno? Dyno. So it's actually Dyno applied to video frames. And there's also some masking. You saw some mask patches here. Masking, self-supervised learning, no labels from video, and it creates this powerful representation extractor. And then they use this for robot actions and poses and many different things. This is VJEPA. Potential applications, so robotic assistants, wearable assistants, and so on. Of course, there are biology, science, multimodal foundation models. AlphaFold can predict 3D shapes of proteins from the sequence of amino acids. So this is a huge progress, improvement. but I'm not an expert in biology, so I cannot talk about it much. And lastly, we have the sensor and embodied modalities. An early version is Gato from DeepMind. Here you can see that it can combine many different modalities. So this single model can the same network with the same weights can play Atari games, it can caption images, you can chat with it, it can stack blocks with a real robot arm, and much more, deciding based on its context whether to output text, joint torques for the robot, or button presses or other tokens. So Gato is like a, it can do all tasks model. So it's a demonstration of the extreme multimodality, vision, language, robotics, and so on. Yeah, I didn't look at how they do this, but there should be some kind of modality to modality alignment or matching losses. And of course, there should be a massive data set where they train this model. Finally, let's look at the robotic transformer. This is from 2023. It translates vision and language into action. So VLA model, vision, language, and action model. Let's look at the. Okay. So you need a way to encode the actions of the robot, and these are encoded as positional change and rotational change. Of course, this is just one example of in the whole space of robot actions. There is also gripping action, other actions, right? The strength that you apply in the gripping action. But at the end, in all, so the central common approach to all these multimodals seem to be you have different modalities. What you do is you convert it to a sequence using patchification, tokenization, and then you embed those tokens into a space where the LLM can understand. And then the rest is autoregressive modeling. This is like the common theme behind all these different multimodal models. It can answer images, answer questions about images, and it can also produce actions given images. So we call such models as VLA, Vision Language Action models. Okay, any other cool multimodal models that you know? We can check. Yeah. NVIDIA Cosmos. What does it do? Okay. Yes.
Also has some very useful minor data.
So it can predict actions from visual input. Translates from translates simulation to real life. I think something like that. Cosmos reason. Again, you can chat about the video image. This is cool. Yes. Any other multimodal models that you want to mention? Nobody?
So that's it's really like translating, which is like kind of text to yes, like short videos, and translate them real time, but with the speakers on voice. Like
I think I saw it, yes, but what was the name?
I think it's I looked at
Real time.
Meta AI.
Real time. I think Gemini also released such a real time. I think it was Gemini. Yes, this is five days ago. I think, is it this one? This is the one I saw.
Mine was Meta.
Meta, okay.
Yeah, I saw.
Yeah, these look easy and boring, right? Real-time translation. It can be done. But of course, lots of engineering has to be done to make this work.
Weird thing is that it uses the own voice
Hmm.
of the creative. So basically,
Okay.
it takes my voice and
Yes.
translates it accordingly.
And it does it in real time.
Yes.
Amazing. Yeah.
The voice part is that stays.
Okay. Hmm. I agree with you. Okay, that was it for today. Foundation models and multimodal models. Hmm?
How is Google using for these models? Yes. Caption.
There are lots of speech-to-text models, even before deep learning. So not as good as this one, but yes. And it's getting better. So 3 years ago, YouTube captioning was not this good, but now it's really good. Okay, let me stop this and then give you the quiz. Huh? Tamam, bakayım.